Okay, so for this video, what we're going to talk about is how we use the Nernst equation to solve for our equilibrium constant based on our voltage. So when we have our equilibrium constant, we had our Nernst equation, which was related to Q. So let's write out our Nernst equation. So that said your cell potential is equal to your standard cell potential minus RT over NF. And we said Ln of Q. So that was the Nernst equation. We also said that at equilibrium, our voltage equaled 0. And at equilibrium, also, our Q equals KEQ. So when we plug that in, the 0 in for our voltage and KEQ in for Q, we get that 0 equals our standard cell potential minus RT over NF Ln of KEQ. Which is nice because then when we rearrange, we get that our cell potential, our standard cell potential, is equal to RT over NF Ln of KEQ. So our standard cell potential, is going to be equal to our natural log, our KEQ, multiplied by this value right here. Which is kind of nice because now we can go forward and back. We can be given our cell potential and we can calculate our KEQ, or we can give our KEQ and we can calculate our cell potential. So, this is under standard conditions too, the cell potential under standard conditions. But it can be equilibrium at any point. So, we're going to look at number 76, and we're going to use this equation right here. And then how we relate delta G to our standard cell potential. And we're going to solve for these values, just given some half reactions. Okay. So on number 76, they give us the following cell. Au 3 plus 3 electrons go into Au. And they say that your standard cell potential of that reaction, is equal to 1.50 volts. And then they also give you that TL, tellurinium, plus a single electron, TL plus 1 electron, goes to TL. And the cell potential for that is equal to negative 0.34 volts. Okay. So it wants you to figure out what your standard cell potential is, delta G naught, and K EQ for the reaction at 25 degrees Celsius. And then it also asks you to calculate the cell potential if the concentrations are different than standard conditions. So let's go ahead and do that. Let's do part A first. So part A, we want our standard cell potential. Well, that one's pretty straightforward. All I got to do is flip around this thing because I want this one to lose electrons and this one to gain. So when I do that, when I flip it and write TL going to, and I'm going to multiply it by 3 as well. TL plus 3 electrons, I get that my voltage is now positive. Perfect. Now I can add those together. So my standard cell potential is 1.84 volts. Remember, standard conditions is 1 atmosphere, 1 molar, 25 degrees Celsius. Okay, so now let's do B. Now, B says I want to solve for delta G and K. So for delta G, we can use the delta G naught, we want delta G naught, sorry, equals negative N F E naught. So that's easy enough. So negative N, well, I got 3 electrons involved. 3 here, 3 here. Perfect. So I got delta G naught equals negative 3 times Faraday's constant, 96,485 volts. Sorry, not volts, joules per volt per mole. And my voltage is 1.84 volts. Okay, that's easy enough. Just plug and chug. 3 times 96,485 times 1.84. Now I'm just immediately going to change to kilojoules. 533 negative 533 kilojoules per mole. So there is my Gibbs free energy. Now I need to solve for my KEQ. So KEQ, well, we know that the standard cell potential is going to equal, we said RT over NF ln of KEQ. Okay. So I am going to simplify this whole RT over F. Because R is 8.314. F, Faraday's constant, is 96,485. Whenever the temperature is 25 degrees Celsius, it will always be 298. So I'm going to plug those numbers in first and then just have that as a number over N, just to make life a little bit simpler so you don't always have to do the same plugging and chugging the whole time. So E naught of the cell is going to equal, so 8.314 times 298 divided by 96,485. Which, and I'm double checking to make sure that I got this number right, because they do it in the book as well. They're just like, here, when you're using this, here's a useful number so that you don't always have to plug them in. I got a different value than what they did, so I did something wrong. time. Oh, let me see if my gas law constant is right. Yeah. So with the gas law constant, here we go. We're just going to write the value down. 0.0591 over N, and then you just do the ln of KEQ. So for this problem, you're going to plug in your cell potential, plug in your N. So your cell potential is 1.84 volts equals 0.0591 divided by, we had 3 electrons, 3, and then ln of KEQ. Get it all by itself. So multiply and divide times 3 divided by 0.0591. So I get 777 equals ln of KEQ. To cancel out ln, I need to take e raised to both of that. So I need to take e to the power of 777. The x on that, it's going to give me an error. So you know what? I'm just going to write this as KEQ equals e to the 777th power. Massively huge number. There we go. So that's how you do and solve for KEQ. Now, if you wanted to solve for different concentrations, you need to plug this back into the Nernst equation, not into this. And for part C, and I have an example of how to solve that, you need to use that your cell potential is equal to your standard cell potential minus RT over NF, ln of Q. But since it's at 25 degrees, you can use 0.0591 divided by N, ln of Q. So that's how you would do part C. You would use that. You would need to write your equation out, making sure that you have, this would be 3, that your TL plus is cubed concentration, and your concentration of your gold 3 plus is just raised to the first power. That's the only thing you need to be careful of on that.